Good morning. So I'd like to start talking about Chapter 9 in your textbook. So Chapter 9 is on physical influences on reactions, and it sort of deals with basically the practical aspects of running reactions and the practical aspects of synthetic organic chemistry. So I've decided to kind of put my own take on that and talk about some factors that affect how you run reactions in the laboratory and how you go ahead and take control of your chemistry and really apply some of the knowledge that we got when we talked about rates of reactions and kinetics. So let's go ahead and imagine the following reaction. This is a reaction that would really occur, but all of the data that I'm going to make up today are hypothetical. So imagine for a moment that you want to go ahead and form an ether. And you have, let's say, the sodium salt of phenol. And you have let's say this alkyl chloride, and you want to do a Williamson ether synthesis, and let's just say we run this reaction in ethanol at 25 degrees Celsius, and that our goal then is to go ahead and synthesize the product in which we've formed a bond between the phenol group and the alkyl halide group, like so. And if I want to be a good person, which I only sometimes am, I might write a balanced equation and point out that sodium chloride is the other byproduct of the reaction. But since I'm an organic chemist, I probably forget about byproducts here. So okay, and just to lend a little bit more specifics to this hypothetical example, let's say we're running this reaction on a 1 millimole scale. 1 millimole scale is a nice scale to run a reaction if you're trying to develop some conditions or trying to work out a synthetic method. Doesn't use that much material, allows quick workup, allows you a reasonable volume of solvent, gives you enough material to weigh out easily, and so forth. So let's say I'm running this reaction with 1 millimole of sodium phenolate and 1 millimole of my alkyl chloride, and let's just say I'm running this reaction in 20 mils of ethanol. 20 mils is a nice reaction volume. You can run it in a 25 mil or 50 mil round bottom flask. All right. Since I'm going to go ahead and draw things out schematically, let's call our sodium phenolate A as a reactant, and we'll talk about our alkyl chloride as B, and we'll talk about our product as C. And if you wanted to, we could call the byproduct D. All right. So imagine for a moment, how many of you are in research laboratories? All right, imagine for a moment you want to go ahead and you do this reaction. So you go ahead, it's 10 a.m., and you set up this reaction. And as soon as you set it up, you take a TLC. And so here's my little schematic diagram of a TLC plate. And this is a nice reaction to run because if you're working with a UV lamp, each of your reactants has a nice chromophore. TLC works if you don't stain. It works that you have a lamp that emits light at 254 nanometers. You have a plate with a fluorophore that when it absorbs light at 254 nanometers emits a greenish light. And if you have a compound that also absorbs at 254 nanometers, and many organic compounds, many aromatic compounds do, then it acts like sunscreen and blocks the UV light, and you don't get the green glow, so you see a dark spot. By the way, this principle is no different than what you have in the fluorescent lights up here. You have a mercury discharge, an electrical discharge through mercury vapor. The electrical discharge through the mercury vapor emits light at that characteristic wavelength of mercury, 254 nanometers. And the fluorophore in the lights coating the glass translates that to white light. It's a mixture of different fluorophores, and we get white light. And on your TLC plate, you get green light, and you see a dark spot. So let's just say that our phenol, maybe it has a lower RF, and our alkyl chloride, maybe a higher RF. And you've set this thing up at 10 in the morning, and then you say, all right, let's see how my reaction's doing. So at 11 o'clock, you go ahead, you monitor your reaction, and you see nice big spots for A and B, and a teeny tiny little dot for C. And so you go off to class, and you come back, and all excited, you check your reaction at 3 o'clock. And your spot is a little bit bigger, like so. And you go and you do some other stuff. And at 8 o'clock, you go ahead and you check your reaction, and your spot associated with the product is a little bit bigger. Sympathy here, a little bit of pain, familiarity here. Okay. So the next morning, you come in all excited on day 2. It's 8 a.m. You run your TLC, and the spot's a little bit bigger. And you go about your day. And now it's 8 p.m. And you run your TLC, and the spot's still a little bit bigger. And you come back on day 3. This is getting old. At 8 a.m., you come in, now maybe a little bit discouraged. And your spot's still a little bit bigger, but by no means is your reaction at completion. And so here is a common conundrum that many of us face in the laboratory. And the most effective people in synthetic organic chemistry are the ones who can take charge of their reactions and make the chemistry work the way you want to work on a reasonable time scale. In other words, we've got the problem, what can be done to make this reaction go to completion? Ideas, help me out. Heat it. Heat that sucker. All right, what else? So heat is one parameter we can control. Concentration. What else can we do to make that sucker go? What other parameters do we have to control in this Williamson ether synthesis? How much solvent? So that's kind of a corollary with concentration. Other factors that we can do, changes we can make to still get the same product. What other parameters did we have in that reaction? What conditions did we use? What was the halide we used? Chloride. So we have our leaving group. What was the metal counterion? Sodium. So we have our counterion. So we have a choice.
So how does the counterion affect?
How does the counterion affect it? We're going to get to that. What else can we control? What do we run the reaction in?
Oh, like solvent conditions?
Solvent, that's another one. So we get all of these parameters that we have to control, even though we still want to form the same bonds, right? We don't have a choice. I mean, we could reroute the synthesis, but we're not trying to do that. We're not trying to change that we're forming an oxygen-carbon bond. We're not trying to change that we're using phenol, not nitrophenol or chlorophenol. We're not trying to change that we have this 3-methoxy, 4-methoxy, 3-p-methoxyphenyl, 1-chloropropane group. All right. So in talking about all of this, and in talking about taking charge of the reaction, what are we assuming about the reaction? What are some of the basic underlying assumptions that I've made in saying we ought to be able to make this reaction go to completion? That it's what?
An equilibrium.
That it's an equilibrium. Yeah. Do most people think this reaction's an equilibrium one? You're shaking your head.
I wouldn't think I would put an equilibrium for this situation.
I would be. So we are assuming something. We're assuming that it can go to completion, right? So I guess my assumption here, maybe there's nothing wrong with this TLC. Maybe this is as good as it gets. I'm kind of assuming that it's not an equilibrium, that the reaction is irreversible, not an equilibrium. If it's an equilibrium, there are some different issues here. In other words, I'm assuming that sodium chloride plus the ether does not go to sodium phenoxide plus the chloride. I'm reasonably confident that that's probably not. If a sophomore wrote on an undergraduate exam, sodium chloride plus an ether goes to the sodium salt, the sodium alkoxide, plus the chloride, I'd probably say, no, it doesn't look reasonable. We've seen examples. We've seen really special, I mean, it's not a crazy idea. We've seen close examples, and I think you saw this, we may have talked about it in the homework, on the Krapcho conditions for cleaving an ester. The Krapcho conditions for most ester cleavage is hydrolytic. Most of the times, if you want to convert an ester to a carboxylic acid, you go ahead, you take the ester, you throw in sodium hydroxide, you get a tack of hydroxide at the carbonyl, tetrahedral intermediate, breakdown of the carboxylate, expulsion of alkoxide anion. That would be the standard way. The alternative conditions, which don't look that far apart from what you're talking about, although there's several pKa units of difference, is you take an ester, like a methyl ester, maybe an ethyl ester, you heat the heck out of it in a dipolar aprotic solvent with lithium chloride. So in other words, here would be an example of the reverse. you would go ahead and take, say, methyl benzoate. I'll just give us a simple example. And you would heat the heck out of it with lithium chloride in a solvent like DMSO. And by heat the heck out of it, I mean probably 150 degrees or 200 degrees. And you would get the carboxylate lithium salt and methyl chloride. So, you know, at first glance, you might say, oh, that's actually, because that's the exact reverse of a nucleophilic attack of the carboxylate on methyl chloride. There are a few differences here. One, we're talking very extreme heating. Another big difference is if you think about leaving group ability. So a carboxylate, pK of the conjugate acid of carboxylic acid is pKa of 5. Phenolate, the pK of the conjugate acid, phenol is about 10. So we've got 5 orders of magnitude, 100,000-fold roughly worse leaving group here. So, okay, so it's not completely crazy to say it could be an equilibrium. So you've got a reasonable point. If it's an equilibrium, we are going to be in a situation where if you waited forever, if it's an equilibrium, you'd be in a situation where, yeah, this would be whatever the equilibrium lay would be as good as it got if you waited forever. So this would be equilibrium only for this plate. What I'm assuming here is that if you wait for forever, you know, well beyond your graduation, it's going to look like this. So this would be irreversible. Maybe not well beyond your graduation. But that lies the conundrum. So yeah, right, we're assuming it's not an equilibrium. If it were an equilibrium, you'd have some different parameters, because then you could drive the equilibrium in a couple of ways. You could drive it by making it more concentrated, just use mass action. Another way you can drive it is by taking one of the products out. And I've had an SN2 displacement like that, which was really cool. It was an SN2 displacement of dimethyl sulfide and an alkyl chloride. Dimethyl sulfide, so if you can picture the nucleophile, CH3,2S, and an alkyl chloride, that reaction was fun because that reaction, I did it in pentane where the salt precipitated out. Let me write the actual reaction. I'll write this. So it was, I'm just going to write, well, I'll write what it was here. It was an acylsilane, and it was the bromo compound. And the product of reaction is the sulfonium salt. So it is indeed an SN2 displacement reaction. You get a sulfonium salt. And this reaction was a lot of fun because when I did this reaction in pentane, which was the solvent I used, the salt, actually I think I did it in neat dimethyl sulfide, but it was a nonpolar solvent. Maybe I did in pentane and dimethyl sulfide. The salt precipitated out as a white solid. When I took that salt up in deuterochloroform to take an NMR spectrum, first I saw my product. When I let the NMR tube sit, it went back to the reactants, and you saw at least an equilibrium concentration of the reactants. In other words, the bromide came back in SN2. So perfect example of using Le Chatelier's principle to drive a reaction. All right, but let's come back to this persnickety example where I'm pretty confident that the reverse reaction isn't occurring. All right, what are we assuming about this reaction? What is the mechanism? What type of reaction are we assuming here? And for that matter, what type are we assuming in the sulfonium salt?
We're assuming that the nucleophilic oxygen can displace the halide.
That the mechanism involves displacement SN2. So we are assuming SN2. And if it's SN2, what do we expect for the kinetics? What would we describe the kinetics as? second order, bimolecular kinetics. In other words, we're assuming that in the rate determining step, A plus B goes to C plus, if you want, I'll say D, the sodium chloride. And we are assuming then that D concentration C dt equals to some rate constant A times the concentration of A times the concentration of B. So usually when we learn kinetics, it ends up being sort of this very abstract thing that's separated from the practicalities of running into the lab and having your darn reaction not go to completion. And all of this, shall we say, book knowledge is really something that you want to keep in your head when you're in the laboratory. So I want to talk now about the effective concentration on the percent completion with bimolecular kinetics. And I want to imagine the problem that we're facing here, just based on the size of those TLC spots. I don't think we got even up to 30% conversion. Obviously, that was my hypothetical example. And ideally, you'd like the reaction to go to 100.000% completion. In practice, you never quite, it's asymptotic, but you want to get darn close. You'd want to get to 99%, basically make those other spots disappear. You know, then if it was clean, you wouldn't even have to do any purification or minimal purification. 90% you're going to still be noticing on the TLC plate, but it's a good starting point. So I want to give us a hypothetical example, and this example may be a little bit different than my drawing. This is the percent completion, and I'm going to make a graph here. And so at the top of the graph, I'm going to put 100%. And I'm going to go ahead and draw a little dotted line as a guideline for 90%. And I'm going to put time on the x-axis, and we'll talk about the time as 1, 2, 3, and 4. Yeah, the arbitrary units, but maybe in the case we're looking at, maybe that's days that we're looking at. All right. Did anybody happen to notice the concentration that we ran the reaction at? What molarity is it that we ran our hypothetical reaction? So it was 1 millimole of each component in 20 mils of solvent. 0.05. We ran that reaction at 0.05. So let's just say hypothetically that we look at the time to 90% completion. And as I said, this may be a little bit different than my TLC plate. And at 0.5 molar, let's just say it was 4 days. And I'll try to draw a curve. I'm going to, in just a moment, I'm going to pass out, Stan will pass out a handout that actually has the calculations done. But I want us to draw a curve about like this, where at 0.05 molar, it takes us about 4 days or 4 time units to go 90% to completion. Now imagine for a moment that we ran the reaction twice as concentrated. If you run the reaction twice as concentrated, it goes 4 times as fast, but the concentration of product, you're using half the volume, so that throws in a factor of 2. So instead of taking 4 days to get to 90% completion, it takes 2 days. In other words, if I want to go ahead and draw my graph here, I'm going to make that curve hit at about 2 days and come on up like this and cross like so. So that's what would happen if I ran it at 0.1 molar. And if I ran this reaction twice as concentrated still, in other words, if I ran it only in 5 mils of solvent, and assuming it was bimolecular kinetics, then you would expect us to reach that 90% point in 1 day. And so by the time you're 4 days out, you're well on your way to being at least acceptably completed. In other words, that very simple choice that we made when we set up the reaction of how much solvent to use for this bimolecular reaction has profound consequences on the course of our day coming back from class and so forth. Generally, for a reaction that's bimolecular, unless there's something tricky about it, running it at 0.2 to 0.5 molar is a good sort of choice of concentrations. Now, as I said, that's sort of a, there we go. Stan, you want to hand out the handouts here? So, all right, so that's simply perhaps a nicer version of this calculated out for your notes. And it's really something very, very valuable to keep in mind when you're setting up reactions is that little choice of how much solvent to use could have an effect of fourfold or longer on the time to reaction. All right, another choice that you get is equivalence, is stoichiometry. All right, so same example. Reaction with bimolecular kinetics. There is a very good reason, if possible, to use a small excess or not so small excess of one component. As you get to this point where you're at 90% done, our concentration has dropped. So basically, in that example we set up at 0.05 molar, by the time you're at 90% completion, the concentration of your reactants has dropped from 0.05 molar to 0.05 to 0.005 molar. In other words, your reaction with bimolecular kinetics is running 100 times slower. 100 times slower. If you're trying to get to the finish line, if you want that spot, those spots of A and B to pretty much disappear, let's call that threshold limit 1%, where you can say, all right, well, the reaction's gone 99% of the way. I could work it up and just strip it down if there are no byproducts and have my stuff reasonably pure without any other purification. I might even be able to skip running a column or doing some recrystallization at that step. If you want to be 99% and you're waiting for that TLC spot to disappear, at the end, it is darn slow, and nothing is wrong with your chemistry. If the reaction is not in equilibrium, and I hear the complaint all the time, oh, my reaction won't go to completion. Well, in the case of bimolecular kinetics, there's nothing wrong with your reaction. It is the nature of the beast. As you're approaching the finish line, you are getting slower and slower. This is one reason why often, if you can use an excess of one component, particularly a component that can be washed away in workup or evaporated or is otherwise inexpensive, you can go ahead and drive your reaction to completion much faster. Because now, if at this 90% point, you are down to 0.005 molar of one reactant, but you still have 0.015 molar or 0.025 molar of the other component, your reaction's chugging away much faster. So again, for our A plus B goes to C reaction, let us consider the situation where we run with a small excess of the sodium phenolate. Phenol is cheap, phenol is readily available, and the phenol could be extracted out by liquid-liquid extraction. And so let us go ahead and say, here's our two components. We've got our A component and our B component, and I'm going to look at the A to B ratio, and we're going to look at the time to go to 90% and the time to go, bless you, to 99%. And this is just what you would expect for bimolecular kinetics. In our hypothetical example, where we're using 1-to-1, I said, all right, imagine under some conditions it takes 4 units, 4 days, for example, to reach 90%. Anyone want to take a guess at how long you would expect it to take to reach 99% completion?
Like 40 days.
You got it. Right on. 44 days. "40 days and 40 nights, 44 days and 44 nights to reach 99% completion." There's nothing wrong with your reaction. It's doing exactly what it's supposed to do. All right. This is one of the reasons why often people add a little bit excess. And it really helps you out at the end when you're chugging along and you still have plenty or still have a sufficient amount of one component. If you go to 1.05 equivalents, the effect to get to 90% isn't very impressive. 3.2 days in this hypothetical reaction, 3.2 units. But to get the rest of the way to 99%, 16. If you go ahead, and as I said, phenol is cheap, and you go ahead and you use, let's go to 1.2. I don't need to do everything. Let's go to 1.2 equivalents. The time to reach 90% cuts down in half, but the time to reach 99% cuts down by almost a factor of 8. And that's just the bimolecular kinetics.
How are you doing the calculation?
The calculations here and here are simply from an integrated rate equation. So remember the equation dC dt is equal to K, concentration A, concentration B, and the concentration C. Concentration A equals concentration A naught minus concentration C and concentration. So this becomes A naught minus concentration of C, and this becomes B naught minus concentration of C. And then we go ahead and say, let's see, we integrate dC from 0 to T is equal to K times integral A naught minus C B naught minus C from 0 to T. I think that's the setup on the calculus correctly. So basically, this is integrated rate equations. Tell you the truth, I usually cheat. I usually just use numerical methods and make a spreadsheet. How many people use like Mathematica or MathCAD or any sort of mathematical calculation program?
I use Excel.
You use Excel, all right. I did, good. I did these calculations in Excel using numerical methods, which basically said, let's forget about the D's, we're going to increment by delta time. So that's how I generated it. All right. Things get even better if you go up to 1.5 equivalents. You go to 1.5 to 1. Now it's 1.2 time units, 1.2 days or whatever to get to 90%, and 3 time units to get to 99%. In other words, if you can go ahead and get away with it without it messing up other things like, leading to side reactions or leading to a product that's hard to remove, basically, to reach that 99%, I've cut my time by more than a factor of 10 by using 1.5 equivalents. And even the more modest, using 1.2 equivalents, gets me pretty close. Just for the heck of it, I'll put in 2 to 1 as an example, and then it's 0.76 to get to 90%, and 1.7 to get to 99%. And I put that here. That's the flip side on your graph here. So that's the flip side on your graph here, is just these integrated kinetic curves for the examples I've shown. But you look at the black curve versus, say, look at the magenta curve. The magenta curve corresponds to 1.2 to 1. And the black curve corresponds to 2 to 1. Or even look at the yellow curve. And look at the asymptote there. In other words, with the magenta curve, you can look and say, it's going to be a long time of coming back and checking my TLC. Even with the yellow curve, you're approaching that asymptote of 100% so much more quickly with the 1.5 equivalents. As I said, nothing wrong with your reaction. Your reaction is just doing exactly what it ought to do. All right. Other ways to speed up the reaction. So, if we look more broadly, you've got a choice of counterion. You could have the sodium as counterion, lithium, potassium, cesium. Cesium carbonate's a good base that's widely used. Phenol, pKa about 10, can be deprotonated with carbonate. It can be deprotonated with hydroxide. If I were doing this reaction, I would probably use sodium hydroxide in the example we talked about to make the sodium phenolate salt. If I wanted the potassium salt, I'd probably use potassium hydroxide. And then on the other end of the spectrum, we have the choice of leaving group. In general, for our leaving group, iodide is greater than bromide, is faster than chloride. In other words, a better leaving group also can speed up the reaction. If I have a choice using a bromide and an SN2 or chloride, probably go with the bromide. If I have the iodide handy, probably go with the iodide. Sometimes people will add, it sometimes can help, you can add in iodide as a nucleophilic catalyst, and that can go ahead and drive the reaction faster. Another really nice reaction is called the Finkelstein reaction, where you can make an iodide from a chloride or a bromide. Acetone dissolves sodium iodide, but it doesn't dissolve sodium chloride or sodium bromide. Acetone's also a good solvent for SN2 reactions. If you dissolve sodium or potassium iodide in acetone and add your chloride or bromide, sodium chloride or bromide come out like snow. It's like a little snow globe in the reaction, and you get the iodide. It's a very nice, quick and dirty way to make the iodide. That can speed you along. Counterion is also important. So the thing that you're trying to do is have a naked anion. The more naked, the better. The more naked that anion is, the more it's available to react in SN2. The more tightly ion paired it is, the less it's available. In general, that means as you move down the periodic table of alkali metals, you get more dissociated ion pairs. Cesium is often better than potassium, is often better than sodium, and that's often better than lithium at giving a naked ion. There are various things that you can add to go ahead and help sequester a cation. One of these are crown ethers. Crown ethers bind cations. Pedersen first discovered this. I think he was at DuPont. I've forgotten his first name. Pedersen discovered this phenomenon with acyclic compounds that were based on ethylene glycol oligomers. And if you have an acyclic ethylene glycol compound, a polyether, it's good at binding cations. If you go to a cyclic compound, and this is where Donald Cram and Jean-Marie Lane came in and won the Nobel Prize collectively, all three of them in 1987, you come up with what's called a crown ether. If you look at the conformation of the molecule, it's kind of crown-like. And the crown ether, this one's called 18 crown 6, reflecting the 18 atoms and the 6 oxygens, is very good at coordinating potassium and giving you a more naked anion. 15 crown 5 is good for sodium, 5th sodium. I'll just write Na+. So crown ethers are sometimes used as additives in reactions. Another very, very big effect is solvent. And big effect is dipolar aprotic solvents are very good for reactions that involve anions, like this reaction, because they're very good at solvating the cation. So they're good at solvating the cation, but leaving the anion naked. So by dipolar aprotic solvents, a classic example would be dimethyl sulfoxide. Dimethyl sulfoxide has a nice dipole to it, so your metal ion gets happily solvated but your anion remains available. Other dipolar aprotic solvents include DMF, hexamethyl phosphoric triamide, HMPT or HMPA it's sometimes called, is another one. Even plain old acetone can be a good dipolar aprotic solvent. Now, in general, if you're trying to dissolve a salt, you need to be able to stabilize the ions. In general, you can't just say, all right, I'm going to dissolve a salt in benzene. Water's good at dissolving salts. Alcohols are pretty good at dissolving salts. We used ethanol as our example. And so in ethanol, again, you get, and this is just sort of a cartoon of the solvent, right? You've got your lone pairs on the solvent. The solvent solvating the metal, creating a coordination sphere. The problem with alcohols is they also solvate the anion. And remember, our goal was to get naked here. Our goal was to get the anion so it is naked and available to react, not tied up. And the problem is, if you've got an alcohol solvent, it ties up the anion and makes it less nucleophilic. Dipolar aprotic solvents are good at the cation, good at solvating the cation, leave the anion available. I'll give you one example. All right, if we take, and this is a different example, but it's the same basic principle. Sodium cyanide does SN2 displacement. If we go ahead and take sodium cyanide, I don't remember what chloride it was, and you take ethanol water as a solvent, and you do an SN2 displacement, this particular example takes about a day to go to completion. If we take the same alkyl chloride and we take sodium cyanide in DMSO, this reaction takes about an hour. That's a big difference. All right, well, there were a few other examples I wanted to give you. I think I'll start out next time by talking about a couple of other examples of effects of conditions on reaction rates. But I think this is a good stopping point for now. So I will see you on Monday, I guess.